Today I'll talk about different methods that I've invented for scientific computing to study a whole variety of problems. And so to give an outline of my talk, first I'll try to describe some of the physical principles that might go into guiding how to discretize physical equations and place them on a computer, and some of the creativity that might come into that process. And following that, I'll just go through 4 of my methods that I've implemented for a variety of techniques. So I'll talk a little bit about fuzzy dark matter simulations and how you can solve them with spectral methods. So this was the focus of my talk yesterday at NYU. Then I'll go into other, so I'll get behind the numerical methods that go into that. Then I'll talk about different methods, including how you can actually take the similar equations, the Schrodinger equations, and discretize them with using smooth particle hydrodynamics. Following that, I'll look into moving mesh magnetohydrodynamics and how you can preserve the Galilean-invariant properties of these equations using a moving mesh. And finally, I'll go into something different. I'll talk about collisionless dynamics and solving that on a lattice. And so why are we thinking about new ways to discretize physical equations? I'd like to motivate this talk by giving an example, a very simple example of the Earth orbiting around the Sun. And you can solve its equations just using Newton's law of gravity. But when you put it on a computer, you have to discretize in space and in time. And you might solve for the orbits of the Earth. And here I'm showing 2 different methods. One is a 4th order scheme, a Runge-Kutta scheme. And the second method on the right in blue is a 2nd order scheme, so it's lower order accuracy, but it's a leapfrog scheme. And what that means is that it preserves the symplectic nature of the equations. It's energy conserving. And so you have different errors due to the truncation and roundoff in these simulations. So you can see that the second method preserves physical symmetry in the equation, and so its numerical effect, here it's exaggerated, but its effect is precession, which is arguably a better numerical bias, systematic bias to have than in this former case with the Runge-Kutta simulation, where you have in-spiral and loss of energy. And so how you discretize your equations matters. So to motivate, let's see if I can go on to the next slide. Okay, so to put things in context, typically when you have a physical system, you have a system of continuous equations, might be PDEs, for example, and these systems will have their own symmetries, their own invariants, conserved quantities, and properties. They might be time reversible, they might be coordinate invariant, they might have energies that have to be preserved. And you put things on a computer. Computer has finite amount of memory, finite amount of computational resources. You have to discretize. And then you can ask, you can think about this discretized system as a new physical system. And you can ask whether you also preserve these symmetries and variants, conserved quantities at the discrete level. So I also like to think about numerical methods as an art, where you might have a physical system, but you have to choose how to represent it. So I'm listing different numerical methods that are commonly used. For example, the simplest one is usually finite difference, where you take your solution and you discretize them onto a grid of points, and you can use these points to estimate gradients and whatnot. And here are more complicated methods, and some generalizations. So for example, finite volume now takes a different representation. This is commonly used for fluid equations. So here you discretize into cells, and each cell keeps volume average quantities, and these cells can exchange material through fluxes. You have finite element methods, which I've also helped design, where you can represent your solution as a sum of these basis functions that have compact support. You can have particle-based methods such as smooth particle hydrodynamics, where each particle represents has a kernel associated with it, and you can smooth out, that can be used to interpolate onto areas in your domain that do not have particles associated with it. And finally, there are spectral methods where you decompose your solution as a superposition of waves, and you can use fast Fourier transforms. It's very efficient for certain problems and highly accurate. It typically has exponential convergence in space. And I've just paired these methods with different famous art pieces to demonstrate how you can think about the world in different ways once you're trying to discretize equations on a computer. So just to illustrate that point a bit more, here's the Flatiron Institute. I have a photo. So we have finite difference methods, which might involve placing values on a point. We have finite volume methods, which might involve taking volume average quantities in these cells. We might have finite element methods, where you have overlapping patches representing your solution. We might have smooth particle hydrodynamics. We have particles out of kernels. It's a little bit less accurate over here. And you might have, you might decompose your solution in terms of waves. So these are actual Fourier collisions. It takes a bit of training to see in Fourier space. And there might be other methods that you can come up with if you're inspired to do so and use your creativity. So these, I just chose a few artistic styles. Here, this one is represented by interacting lines as your fundamental discrete unit. Here we have another illustration. So it's really important to think creatively sometimes, and but also keep in mind that you want some nice robust properties, such as you typically want to test your method always for convergence. So you want to make sure that if you increase the resolution, then you have well-behaved different behavior in your errors that usually converge at least as fast as some power law. You also want to make sure that your method is able to scale in both in the amount of memory that it requires and the amount of computational time. And again, these have to behave according to some power law. Otherwise, it would be impossible to run on supercomputers reasonably. And you want your results to be robust and reproducible. And finally, the point I want to highlight really is that you'd like to conserve as many physical symmetries as possible, and I'll illustrate why this can be important in various contexts. And I'd like to highlight just some of the different applications that numerical methods can be used for. These are actually from my website. So I've used them to study first galaxies, shocks, early the inflaton field, and fuzzy dark matter, and primordial magnetic fields, and so on. So let's begin with spectral methods for fuzzy dark matter. Yesterday I gave a seminar on pioneering simulations of fuzzy dark matter in a fully cosmological context with baryons. And I just want to highlight a bit more the numerical methods that go into that. So we're starting with, in the simplest case, we're just starting with the Schrodinger Poisson equation. Here, Schrodinger equation is linear, but it becomes nonlinear because the potential is ceded by the potential due to self-gravity, just from Poisson's equation. And it turns out that this set of equation is actually ideal for spectral methods, very simple to evolve. So if we convert to Fourier space, then these novelist squared operators just become k squared, and you can evolve your simulation using a series of Fourier transforms. And you can split the effect of the potential and the effect of the kinetic operator into two steps. They don't commute, so you'll have some second order error in time. But here's the simplest scheme one can come up with that involves, it's a second order scheme. It's split into a half time step kick step, followed by a kinetic drift term, and then a repeat of the kick step. So we can calculate the potential in a periodic domain simply by Fourier transforming the density field, dividing by k squared, your wave number, and then inverse transforming that. And then you apply this unitary operator here that involves the wave function to your, that involves the potential to your wave function. And this is followed by similar drift step in Fourier space. So you can transform, apply the kinetic operator. Again, it's a unitary operator. You transform back, and then you have another half-step kick. And a method like this couples very nicely into cosmological codes, which are typically second order, and break up time steps in such a way. So you can then gravitationally couple the dark matter to the gas dynamics, which I'll also talk about. And I'd like to point out that such a discretization and representation of your solution is actually very applicable to quantum computers in the future, something I'd like to think about extending these methods once the technology develops there. Because quantum computers are very powerful. You can have exponentially represent very large amounts of solutions simultaneously. However, they're more difficult to program. They typically involve you to design unitary operators like the ones I'm showing here. And so I'd like to point out it's always important to test your numerical methods. So here, this is here I'm evolving my simulation to some point in time and using some ultra high resolution as a reference solution, just to show that as I'm increasing the resolution, it's second order in time. So here I'm halving the time step, fixing the spatial resolution, and it's exponential in space, which means that here my errors are actually dominated by the time errors, and increasing the resolution may not get you any improvement. I mean, as long as you're resolving all the wave modes of interest. And so you can also just check visually that you're actually resolving your simulation properly. These are actually very hard features to resolve. These are vortex cores, vortex lines in your simulation of fuzzy dark matter, where you have basically zero density, but and a winding number in the phase. And I've just came up with a visualization to visualize them here, and you can see correspondence between these two resolution levels. And finally, you can also perform tests to make sure that your energy is conserved. So for example, here I decomposed the energy into different components. The important one is the total energy E, which does show some oscillation, but due to the unitary nature of the discretization, this energy cannot decay. So, and then these errors, these oscillation amplitude can be controlled by the time step that you choose. A question?
Yeah, sorry, is G a given function?
Oh, sorry, what's that?
Is G a given function at each time step? Or
oh, G.
You didn't describe where G comes from.
Where is G?
Yeah. Well, where does it come from? And you showed that you said G generates the potential V by the Poisson equation, and then V controls the Schrodinger equation. But where does G come from?
Oh, sorry. So here, okay. So here, okay. So that's just a gravitational constant, and the self-potential is seeded by the density distribution. So rho is equal to psi squared here.
Oh, okay.
Yes.
Sorry, I missed
So
the rho.
yeah, I'd like to make that clear.
Okay.
Yes.
Can I ask another question?
Yes. Question in the back.
So you're solving a first order equation in time with the second order time operator, right? You're using a leapfrog.
Yes.
How do you know which mode to continue in your calculation?
Oh, I'm sorry. Can you repeat the question?
How do you know which mode to latch onto in your calculation?
Oh, which mode?
Since you're using a second order differential operator to solve a first order equation, so you get an extra mode, a computational mode.
Okay, so I'd like to point out that the okay, so actually okay, I mean so this is actually a linear equation. If your potential is prescribed not by the self potential, then it's a linear equation, and then in such a case, you can actually have you can actually find exact solutions, exact advections. and the the errors that you get just come from the non-commutativity of the potential with the Hamiltonian operator when you turn the potential into the self-potential. And so
do you use a temporal filter?
there is no filter. So we can talk about extensions of this method some more, but it's actually conceptually it's very similar to leapfrog schemes for n-body simulations. So I'd just like to highlight some of the applications of such a code where you can simulate fuzzy dark matter, couple it to ordinary matter, make predictions of what maybe first galaxies might look like in the early universe, things that we might be able to observe with JWST. And here, one of the main conceptual takeaways is that first galaxies are quite sensitive to the small-scale nature of dark matter. And they're a unique probe for what dark matter could be, because these structures are not yet virialized. They're really providing independent constraints than what low redshift can give you. And other applications of the method include, yesterday I showed how these Schrodinger Poisson equations actually approximate collisionless dynamics, and they also take away some well-known discreteness effects that show up in collisionless simulations, n-body simulations where you have shot noise. So I'm just highlighting down here. Here's a simulation of Schrodinger Poisson simulation on the left and a collisionless simulation on the right, where this collisionless simulation shows this artificial fragmentation of stars. Okay, so I'd like to now talk about solving the Schrodinger equations in a different way, using this smooth particle hydrodynamics formalism. And so the idea here is that you can take your nonlinear Schrodinger equations. Now I've just added a self-interaction term here just for fun, one thing that is sort of cool is that you can rewrite your Schrodinger equation as a fluid equation, shown here in line 2. So you define a density, which is chi-squared. You have your conservation law for density, which is just conservation of probability density that you're used to. And the interesting physics comes in from this momentum equation. You define a velocity, and this velocity is defined as the gradient of your phase. So your wave function is amplitude times e to the I phi. Gradient of the phase defines a velocity, and then you can write down your momentum equation. You get something that looks like a fluid equation. You have, from the self-interaction, you have something that looks like the gradient of a pressure. Your equation of state might be pressure is equal to rho squared. You have your potential, and then finally you have this term, which encapsulates the quantum wave dynamics, and it should encapsulate the uncertainty principle as well. So you define this pressure tensor that is defined in equation 11, which now depends on gradients of the phase. And so it's a non-local pressure, but and it's also, I mean, you have to sensitively estimate these gradients, but in theory there's nothing stopping you, and so it's worth thinking about how to discretize these methods. So this is something I've explored a few years ago, where you can use these SPH kernels. Typically, W is a Gaussian kernel. You discretize your wave function into points. Each point has a mass associated with it, and then you can reconstruct your density at any point as a sum of these particles weighted by the kernel. And then you can come up with discretizations for estimating gradients.
Why would you add viscosity? There is no viscosity in it.
Okay. Yeah, there's no viscosity. So let me talk about that in the end. So there's no viscosity here. There's no viscosity. No. Okay, but you can come up with a discretization for the pressure tensor, and then okay, so then you can. This is one way to do simulations. You can find motions in a harmonic potential as the simplest example. You can find ground states of Bose-Einstein condensates. You can recover Thomas Fermi solutions. And I have this point about the potential. So one of the open problems sometimes in these physical systems is to find ground states. So if you add viscosity, which is something you can easily do in this fluid formulation, you can actually evolve your solution into a ground state if that's what your goal is. So it's that's an application of such a method. And so this particle-based method has actually been adopted by a few other groups, Phil Hopkins, also Nori and Baldi in Axion Gadget, and it's an alternative way someone can study fuzzy dark matter. So I'd like, oh yes, question.
Can you comment on the convergence rate of smooth particle hydrodynamics and
good
and
question.
why you wouldn't just solve the nonlinear Schrodinger equation using a spectral method like you did before?
Okay, yeah, so the spectral method has an excellent convergence rate. So I actually prefer to use that method. Smooth particle hydrodynamics does not have, so formally, theoretically, its convergence rate is not well defined. I actually have some tests, though. So here in this test problem, I do get a second order convergence rate, but it's not clear to me that a priori that it's going to be well behaved. So I chose to actually run my simulations with the spectral method, so I have robust reference solutions, and I'd be keen on extending these smooth particle hydrodynamics to the cosmological simulations as well, because in a sense they're computationally more efficient. But I'd like to also make sure that they're robust. And there are some potential things you need to watch out for in your solution. You can have, the Schrodinger equation does allow for infinite velocities at points of zero density. So that's much easier to handle with the spectral method. Okay, so again, I don't just have dark matter in my simulations, I have gas as well, and these typically obey the magnetohydrodynamic equation, so I just wanted to spend a few slides talking about different ways to discretize the fluid equations. So two key ways are Eulerian schemes, where you divide your, you have a lab frame and you divide your volume into these cells, they exchange fluxes, so you discretize space. These methods are great for capturing shocks. The alternative class is Lagrangian schemes like smooth particle hydrodynamics. Here you discretize mass and you follow the particles as they move with their velocities. So it's Lagrangian, it's fully adaptive. Particles follow where the mass density goes. And typically these methods have a harder time though with dealing with shocks. And so I'd like to point out the Lagrangian is Galilean-invariant, which means if you boost your reference frame, it's not going to change the truncation errors. So I'd like to say that the truncation errors are Galilean-invariant in Lagrangian schemes, and this is not true for Eulerian schemes. And so, so state of the art for Eulerian schemes would be methods like adaptive mesh refinement, which can zoom in on small features in your solution. For Lagrangian schemes, you have smooth particle hydrodynamics, which are great at handling areas with vacuum boundary conditions, open space. And what I work on is an intersection of the two methods, which uses it's a moving mesh framework, where we have these quasi-Lagrangian mesh generating points that adaptively change your mesh. But because of the finite volume nature, you can capture shocks quite effectively. So it's both adaptive. It can capture things like advection exactly without dissipation. So this code. My work is built into the Eurepo code, which was designed by Volker Springel in 2010, designed to handle the Euler equations with self-gravity, and has these nice properties that I've been describing. And just some here are some movies from Volcker showing just conceptually how such code behaves. And so part of my work is to accurately solve the equations for magnetohydrodynamics on this moving mesh. What happens when you add in magnetic fields? Naively, I've written the equations down in conservative form. So here I've added the magnetic field. Here is the flux operator. And naively, it just looks like it's just another conserved quantity where you can calculate fluxes. But there's an important principle to maintain, which is the divergence-free condition on the magnetic field. This is one of Maxwell's equations. And it's just a constraint that's not needed to evolve the system, but it's a property that should be true. So if you start off with divergence-free fields, it should always stay divergence-free. And not maintaining this condition can actually lead to significant numerical instability. And so there's the state-of-the-art solution is to use constraint transport algorithms to evolve the magnetic field. And there's a really nice conceptual way how to think about this discretization. And so if you think about what the divergence-free condition means, it means if you have a cell and you calculate the magnetic flux pointing outward from each of these spaces, the sum of these fluxes should be 0. And so in the constraint transport method, you update these fluxes using these circuits, calculating the electromotive force around these circuits in an oriented fashion. So we can just say counterclockwise, or yeah, we can just say clockwise here. So if we calculate this circuit here, corresponding to the space on the right, and add it to the flux, then it's going to change the flux by some amount. Now, if we take this other face here, the face facing forward, and we want the flux pointing outward, we take the circuit, again with the same orientation, so we can take clockwise. So we can see that if we take this edge, there was a contribution from the circuit that was pointing downward that adds on to this face, but the first face, the contribution has the opposite sign because the circuit has the orientation pointing upwards. And so these two changes cancel, so that you can convince yourself that the sum of the fluxes, when you take these 6 faces of the cube, the sum of the fluxes will still add up to 0 because of this cancellation property. So that's the basic motivation here. And this is much harder to do on a moving mesh. So I've thought about different ways to do this. And so on a moving mesh, you typically have polyhedral cells, but they can change their faces, and they can change their number of faces as they evolve. And so the best solution I came up with a few different face methods to solve this problem, but the best solution I found was to so first of all, you can always take you can always play the same game. You can keep track of the flux on a face, and you can take these circuits to calculate the electromotive force in an oriented fashion, and then the contributions will always cancel with neighboring faces, so that the sum of the fluxes is always 0. But it turns out you can actually come up with vector potential formulations that are equivalent to constructing a constraint transport algorithm. So vector potential means that you define this vector A, which the curl of A gives you the magnetic field. And this allows you to go from transform your problem from faces to edges. And ultimately, there is also this second nice property of the Voronoi mesh that I use, which simplifies the calculations, which is instead of working on the polyhedral cells, it's cleaner to work with the dual of the graph, which is this Delaunay triangulation. So this dual of the graph always gives you tetrahedra, which are better behaved. And ultimately, I can keep track of cell-averaged magnetic fields, cell-averaged vector potentials that then allow me to uniquely reconstruct the magnetic field on these tetrahedra in a divergence-free way. And then following that, I have a mapping operator that can then give you back the magnetic field in the cell average of the polyhedra cell. And so why is this important? It's important to maintain, of course, things like the divergence-free nature of the solution. So here's a solution comparing a cleaning scheme, which would be an alternative way to solve the equation, but less numerically robust, and with a constraint transfer scheme. And you can have machine precision control on the divergence. Why would you want this? Okay, so you want this to maintain your Galilean invariance because the cleaning terms are not Galilean invariant. So here I have just the advection of magnetic field loop. This is showing the magnetic energy. It shouldn't actually change, it should just advect. But you can see that the cleaning scheme gives rise to some diffusion of the structure, as does the static nature of the mesh. What you'd also like to have is, see, I'll go to this one. So you'd like to also preserve physical symmetries and invariants of your simulation. So one of the preserved symmetry is the average magnetic field in a box. So these are showing cleaning scheme and constraint transport simulations of turbulence. And if you have a cleaning scheme, you're not guaranteed to maintain this average magnetic field. It can actually exponentially blow up once you are in these very high supersonic regimes, and your magnetic field does not converge in this sense. So we can also test this. I mean, you could see it by eye in the previous slide. You can also test for the convergence of the power spectra. When you have the cleaning scheme, you actually add a lot of large physical scale, small k, power in your solution that does not converge. And this is also seen in simulations of galactic disks, where with cleaning schemes you typically tend to, if you use very high resolution and if the conditions are quite turbulent and somewhat supersonic, and you can build up these large dipole magnetic fields, which are artificial and they're due to the cleaning terms. So you can test for equipartition, and in some cases you cannot find any in the Powell cleaning scheme, whereas you can get equipartition between kinetic energy densities and magnetic fields with the CT scheme. So in summary, I'd like to highlight that the method here that I described, it's divergence-free. It maintains this divergence-free quality of the magnetic field. It's Galilean-invariant, so the errors do not change if I boost the frame. You have nice conservative properties. I also conserve momentum, energy, mass. It's quasi-Lagrangian, and you can handle shocks and automatically adapt to where the mass flows in your simulation. So let me check on time. I think in the interest of time, I'll skip some of the applications to other systems. I'll just point out that we've applied this method to not just cosmological simulations, but also to the study of star formation and turbulence. And so here, we can do things like, in these supersonic regimes, we can have a turbulent box. This is supposed to represent a giant molecular cloud. You can change the magnetic field strength and see how turbulent structures develop as a function of scale down many orders of magnitude, and look at the magnetic field configuration too, and then compare with observations to tell you something about the Alfvénic Mach number in these simulations. And here we found actually two different regimes of collapse of these prestellar cores. There's one where you might start out with a weak field on large scales, and your magnetic field grows actually faster than what you get in a strong field, because the compression is more isotropic. It grows adiabatically as 0 to the 2/3 just from the flux freezing argument. And you can actually get these turbulent morphologies in prestellar cores. This is in contrast to collapse, when you have a strong magnetic field threading your molecular cloud, where you can have slower growth of the magnetic field as you condense and collapse these structures, and you can have these anisotropic and hourglass-like morphologies. And so in the in the next portion of my talk, I'd like to talk about go back to the to collisionless dynamics and the Vlasov Poisson equations, which describe again collisionless dark matter, so cold dark matter. And I'd like to talk about coming up with discretizations that that preserve one particular symmetry, which is time reversibility of these equations. So here I'll talk about how to solve these equations on a lattice. So just to write down the equations, now we have the 6-dimensional distribution function that describes the density, the phase space density as a function of position and velocity and time. And it's covered by equation 15 here, where again, the potential is due to the self-gravity, so it's seated by Poisson's equation. And you can recover things like the physical density by integrating moments. So this equation here is just a statement of conservation of phase space density. And F is constant along trajectories in the system. This is Liouville's theorem. And like I mentioned, it describes systems such as cold dark matter. And so typically, cold dark matter simulations use a Monte Carlo sampling of the n-body techniques for the Poisson for these collisionless Vlasov Poisson equations, and that typically comes with shot noise, and you're limited sometimes in resolving some of the fine phase space structure. So there's real motivation to resolve some of the interesting phase space structure that you can get, which could be important for structure formation, but it has these other applications that I list here as well. And like I said, one of the important symmetries here is the Poincare recurrence theorem, which means that you have this time reversibility property, but actually an additional consequence is that if you start out with a configuration in phase space, after a sufficiently long time, you'll return very closely to that original configuration. And so you start out with Poincare, you get something that's mixed, but you get him back. So here, I'll talk about a little, something that's a discretization that might sound a little bit unusual at first, and quite simple. So we're going to define a set of lattice sites, and your density distribution function, F, is going to live on these lattice sites. And to evolve them, all we're going to do is apply these permutation operators that are going to cyclically permute your space. So the velocity is going to be updated by your acceleration field. And here I've applied this rounding operator, so I'm just rounding to the nearest integer. And it's a way to make sure that the particles stay on these lattice locations. And by increasing the number of lattices, you can actually control this error. This type of error is very different from Monte Carlo shot noise, so it gives you an alternative numerical method with different properties. And one of them is reversibility. And so so similarly, the positions are, well, similarly here again, now using the velocity field and applying these rounding operators. And so I'll just use dimensionless units. So the spacing here can be 1. And so acceleration can be obtained from a Poisson solver, like the one I described in the beginning of my talk using Fourier transform methods. And so just to illustrate this, this lattice, just in the simple one-dimensional case, here we have position, here we have velocity. The kick operator pushes particles, so it pushes each of these columns by a certain amount as a function of x, given by the acceleration from the Poisson solver. And then there's this drift operator that is going to apply the shearing in phase space. And you can alternate these two in a kick, drift, kick fashion to evolve your simulation. So each step is a simple permutation. There's no round-off error. It's reversible, conservative, Lagrangian, and importantly, there's a discrete Hamiltonian that's associated with this finite lattice, which approaches the continuous limit as you increase the resolution. And finally, one interesting behavior is that since you have a finite number of lattice sites, all of your orbits are actually periodic after a sufficiently large number of time. It has to be. And this is maybe not completely physical because in chaotic systems, you might not fully convert, you might not fully close your orbit. You might just return arbitrarily close to your orbit. But this actually, I think this method gives new insights into the study of chaos, because now chaos is converted into arbitrarily long periodic orbits. And so I'd like to just demonstrate some basic tests with this method. So here's the gene's instability, just in one dimension, x and so position, velocity, space. We start out with a Gaussian light profile in the velocity direction. This is collapsing under self-gravity. It's gene's unstable on large scale, and you end up with something that's well mixed. And I'd just like to, for the purposes of this informal talk, I'd like to compare it against other, visually compare it against other informal, against other methods. So here we have integer lattice, t equals 3, t equals 9. Just looking at the phase space distribution. Here we have an n-body technique on a particle mesh scheme. You can see how the noise properties are different. So here we have shot noise due to the Monte Carlo sampling of this distribution. And finally, here we have finite volume on the right column, which shows diffusion at late times. So that's not a good property to have if you're interested in the fine phase space structures. And so I'll just show a few more tests. So here's a Landau damping test where, again, we wind up these spiral arms, and it's going to, this system is going to approximate a smooth equilibrium, but it's never going to reach it because you did not start out from that equilibrium at first. So you just have an infinite number of arms at the end. But if we look at, again, these three schemes, the finite volume actually does reach this equilibrium because of the diffusion that's in the equations. And integer lattice and Monte Carlo methods do not because they conserve energy. And but then again, the noise properties, the error properties of these two simulations are very different because here you're dominated by the shot noise.
So, yeah,
question?
Are you going to discuss, well, convergence again and
yes.
To make a meaningful comparison between these methods, you have to maybe say that they ran for the same amount of CPU time.
Oh, yes.
That the parameters were adjusted to that you can do these three simulations in about the same time. Or that depends on the implementation and all sorts of things.
Yes.
So
I have a bit.
Are you claiming you beat them with the same CPU time, or is this just for illustration?
Well, this is just for illustration here. Turns out, yeah, this is the same resolution. Turns out integer lattice is 10 times more efficient to implement in terms of CPU time because the operators are so simple. You can, but again, so I'll show some tables summarizing some of the properties. Again, it's important to test for convergence and all of these. But first, the qualitative properties are, you can ask whether the method's conservative, whether it's reversible, so integer lattice is the only one that's fully reversible, and whether the method's Galilean-invariant. Yeah, so here are some compute times for, so in this case, the compute time is a factor of 3, smaller for the integer lattice compared to n-body, but I'm not claiming that I've optimized my code. Of course, there might be ways to improve these things, but generally, this is a very simple and elegant method to implement. And so in terms of computational cost, there are, so integer lattice is similar to finite volume in terms of computational cost because you've discretized this space and velocity. Particle mesh scales as the particle number. There's actually, let's see, so I won't get into this today, but there's different ways you can either decrease the amount of memory that you use and but increase the computational cost, or vice versa. But it's definitely competitive with other methods. And if you care about the full phase space distribution, I think nothing really beats n-body if you're just interested in the density distribution. And so I'll skip the slide, but there's other interesting extensions of the model. So you can also study this weakly collisional limit. You can add in a VGK source term and see how that affects phase space. So here is a shock simulation where I'm just showing two different cases, strongly collisional and weakly collisional case, and I'm recovering the shape of these shocks. And shown in the transparent lines are hydrodynamic solutions. So I can show that you can actually recover the Euler equations here, just by adding a weakly collisional term. So it could be interesting to study weakly collisional regimes in astrophysics, such as systems where you have ground pressure stripping, but if you do some back-up-to-envelope calculations, the mean free path of particles might be on order the size of your satellite galaxy, and so you might be in a weakly collisional limit. You can also extend it to plasma physics. So here, just solving the Vlasov Maxwell equations, I just flipped the sign for the Poisson equation, and so now I'm just illustrating here the two-stream instability. And this can give an alternative to particle and cell simulations. Okay, so just to summarize, integer lattice is a very simple, clean method to study the Vlasov Poisson systems that will have unique properties. It changes the nature of the errors, and it's fully reversible. And there might be memory efficient implementations as well. So to conclude this informal lunch talk, I just want to say that designing numerical methods is both, for scientific computing, it's an analytic process. Of course, you have to worry about things like efficiency, accuracy, robustness, but it's also a creative process because you can choose how you discretize your equations and represent it on the computer. So, I hope that by demonstrating these different methods, it helps inspire you to think in new creative ways to come up with new ways to discretize these equations. And so we've just explored 4 different methods today. Of course, lots more out there. And I've highlighted why it might be important to care about, spend some extra time thinking about preserving physical symmetries and invariants in your equation to maintain well-behaved properties in your simulation as you evolve them for large amounts of time. So that concludes my talk for today, and I'm happy to take any questions.